Hi, my name is Andrew Robison, and today I'd like to present to you our work of off-resonance artifacts of common metallic implantable medical device materials in low-field MRI. Before we get started, I'd like to acknowledge that I am an employee of Med Institute Incorporated. We conduct MRI safety testing as well as computational modeling and simulation for numerous medical device companies. It's well known that metallic objects can produce an artifact in MRI. Even for objects that are not magnetic, in the sense the magnetic field of the scanner does not induce an appreciable force or torque on the object. As you can see for the MRI scan of a hip stem on the right. It's also well known that the artifact size is generally related to both the field strength and the magnetic susceptibility of the material. And that means that new commercially available low field MR scanners present new opportunities for improved imaging near metallic implants. So the goal of this work is to quantify the reduction in susceptibility-based image artifact in low field MRI experimentally. To do this, we took 5 metal samples of varying magnetic susceptibilities that you can see on the right. The susceptibilities are all based on a volume basis. We looked at gold, titanium, resoloi, which is a biodegradable magnesium alloy, iron manganese, and a cobalt chrome. Each of the samples were cylindrical and with the same dimensions, with a diameter of 3 millimeters and a length of 5 centimeters. And you can see the representative image of the gold sample on the left. We then placed each of these samples individually parallel to the B field in a copper sulfate phantom. The samples were suspended by a mesh net, as you can see in the image of the phantom. We scanned them then at a 3 Tesla Siemens Prisma scanner, as well as a 0.55 Tesla Siemens Free.Max scanner, using a gradient echo sequence with the same parameters at both field strengths. We then found the worst case image artifact in both the coronal and transverse planes, and are showing the worst case image artifact in the coronal plane for several of the samples on this slide. What we can see is that since the samples were placed parallel to the B field, the greatest image artifact occurs at the ends of the sample where the magnetic field is changed the most due to the presence of the object. We can notice a couple trends that are visible here. The first is that with increasing susceptibility, the image artifact is increased. Also, the image artifact size is increased for each case with the increased field strength. In this slide, you can see the coronal views of the worst case image artifact for the higher susceptibility samples of iron manganese and cobalt chrome. Next, we can look at the results in the transverse plane. What you're seeing here then is for gold, titanium, and the resoloi. And we notice a similar trend that with the exception of gold, we see an increased image artifact size with the field strength. And then we also see an increased image artifact with increasing susceptibility. And then on the next slide, you can see the results for the higher susceptibility samples. In the next slide, we see the results in a plot. On the left are the results for the coronal plane. On the x-axis is the susceptibility of the sample. On the y-axis is the maximum artifact width. The maximum image artifact results are plotted in red for the 0.55 Tesla and in black for the 3 Tesla. So what we can see is that generally the image artifact size increases with susceptibility. And it's also significantly increased with the increasing field strength. And that's true for both the coronal and transverse planes, with the exception of gold, which has a very low absolute value of its susceptibility as expected. Next, we can see the results of the percent reduction by going to a lower field strength. So with the exception of gold in the transverse plane, we're able to get about a 40% reduction in the maximum artifact width simply by going to a lower field strength. And this image artifact could likely be further reduced by careful selection of a different sequence. So to conclude, we have shown that experimentally, the image artifact is significantly reduced at the lower field strength without without changing the sequence. And that this means that the low field MRI could yield improved results near metallic implants. I would like to thank Fort Wayne Metals, especially for providing the samples for this work. And thank you very much for listening.